Thank you everyone for joining us for the fifth Compass lecture of the semester. Feel free to sign in, it sucks if you want. We're super excited today to have Hitoshi Murayama join us for this lecture. Hitoshi Murayama is a well-known theoretical particle physicist who works broadly even on astrophysics, cosmology, and condensed matter physics. He has been a professor in the University of California, Berkeley since 2000, and is also the founding director of the Kavli Institute for the Physics and Mathematics of the Universe at the University of Tokyo, serving from 2007 to 2018. Having been born in Japan, lived in Germany for 4 years and in the US for 21 years, and served on advisory committees around the world, he is a multicultural global denizen. In October 2014, he was invited to give a speech at the United Nations headquarters in New York about how science unites people and brings peace. He received the Yukawa Commemoration Prize in Theoretical Physics and is a fellow of the American Physical Society and the American Academy of Arts and Sciences. Please join me in welcoming Hitoshi.
Thank you. All right. So I'd like to give a talk with the title, When Symmetry Breaks. And what I intend to do in my talk, of course, to eventually connect to my own research in the rest of the department, is an idea that something is common. Oops, it's not moving forward. Hey, what's going on? Okay, so to connect, to find a common theme among the magnets on fridge, cubes of ice, halibut, and rack of laundry. So that's the idea of symmetry. So you all know symmetry is a very important concept in physics. It goes back to Emmy Noether, and she proved the theorem that says that any symmetry will lead to a conservation law, like energy conservation, momentum conservation, angular momentum conservation. And those conserved quantities end up generating symmetry. So they are really worked tightly in hand together. And one thing we know is the laws of physics seem to have very high degrees of symmetry. For example, if you see a galaxy of this orientation, you're bound to see another galaxy of the opposite orientation because laws of physics doesn't seem to distinguish left from right. But there's an exception to the rule like weak interactions, but by and large, the left and right are the same. That is a symmetry called parity. And if you see a galaxy of one orientation, you're also bound to see all other possible orientations of them. And that's because the laws of physics is invariant under rotation of the system. So that would lead to a conservation of angular momentum. And this is actually based on the real data taken by Sloan Digital Sky Survey. LBO also played a major role in this. And looking at the individual galaxies, you can observe and place them in a computer with the right position and right color and right orientation, the right shapes. And then you can pretend that you are doing this flyby in space on your own. And if you would like to actually do this on your own, you have to travel at a speed that is 100 trillion times faster than the speed of light. So don't try this at home. But the point here is that, they're looking at it, again, by and large, universe looks everywhere the same, pretty much the same. No matter how far you go, universe looks pretty much the same, which means that the laws of physics is invariant under translation in space. And that is the reason why momenta are conserved in laws of physics. So that's the translation symmetry. So at the level of the Newton's equation of motion, you can express parity by inverting the signs of one of the coordinates, or you can do rotation, you can do a translation in space, and all of them are symmetries of the laws of physics. So the laws of physics have a very high degree of symmetry. But then comes a question that, well, many of us are right-handed, like 90% of us. Pretty much all of us have our heart on the left-hand side of the body. And so even though the laws of physics is symmetric, that what we see in the daily life doesn't seem to respect that symmetry. So why is that? So if the laws of physics is symmetric, what is the origin of diversity? And at least part of the answer is due to this idea called spontaneous symmetry breaking. And so this is the idea that the system in many of them has a very high degree of symmetry, like our universe. Translationally invariant, rotationally invariant. But if the ground state of the system respects only a subset of that symmetry, then we say the symmetry has been spontaneously broken, and I get to example of that in a moment. And once that happens, there are many degenerate ground states, exactly the same energies, but they are related by the symmetry transformation from one to another. So that's when we say the symmetry is spontaneously broken. So the first example of that is the rack of laundry. So, it's a good idea to let the laundry dry on their own because we have the very dry climate anyway to save carbon production. And when I hang my shirt on the rack, the first shirt, it doesn't matter whether I let the shirt facing left or right. But when I hang the next shirt, if I had hung the first shirt facing left, I have this tendency that I would like to hang my second shirt facing the same way to make it look kind of neat. And after doing all my job of hanging all the laundries, then in the end, I look at the rack and said, oh my goodness, why are all the shirts facing left? And it doesn't matter whether they're facing left or right, because they're totally equivalent to each other. But once you actually have a system, then they end up choosing one direction over another. And so in this case, this parity symmetry between left and right have been spontaneously broken. And same goes with halibut. And halibut, of course, is a fish. It's one of those flat fish. And it's clear why they evolved to have this weird shape of having both eyes on the same side of the body, because they would like to hide in the ocean floor sand to be protected from predators. So they evolved in that way. In fact, when they are born, they look like a regular fish, has one eye on one side of the body, another eye on the other side of the body. But as they grow up, the eyes would migrate to be on the same side of the body so that they can lay flat on the ocean floor. So obviously, the halibut has both eyes on the left-hand side of the body. And again, it doesn't matter if it's on the left side or right side, because you can also find other species of flatfish like flounder, where you see both eyes are on the right-hand side of the body. And I happen to know they are different species because I eat both of them and they taste differently. So they are definitely different species. Halibut has a very clean taste and is great for sushi. Flounder has a little earthy smell, but if you actually simmer in sauce, that's also very delicious. But they are definitely different species. So each species end up choosing one orientation over the other in the course of evolution. It doesn't matter if it's left or right, but they have to choose one if they want to lie on the ocean floor to be protected from the predator. And there are many examples of that in biology. So Keiko Kuroda is one biologist I respect, and she studied conch. That's a shellfish that also winds around in one particular direction, as you see in this picture. And they start to wind around at the early stage when the egg hatches into eggs hatched and divide into 4 cells and 8 cells. Around that time, they start to rotate. So what she did an experiment to prove that, again, left and right has no difference as far as this system is concerned, by nudging the cells to go in the opposite direction. And that's kind of, the brutal thing to do, but nonetheless, you can do that. And in the end, they grew up to a completely healthy, happy conch, adult conch. And of course, once their children are born, the direction is etched into the DNA. So their children would grow up in the normal direction rather than this forced direction of the parents. But nonetheless, this proves the point that, again, it doesn't matter whether the conch winds around in left direction or right direction. That is a notion called chirality in biology. And that is another example of spontaneous symmetry breaking. So in the course of evolution, this particular conch chose to wind around in this the clockwise direction. And that appears in chemistry as well. So if you look at the sugar, oops, I'm sorry. And if you look at the chemical formula for sugar, they have 2 orientations. One is called D-glucose on the left, another is called L-glucose on the right, and they are mirror image to each other. And D-glucose is the sugar we consume, and that's in everything we eat. L-glucose, we actually don't have an enzyme to actually digest it. And it turns out that entire biomass on our planet can digest only D-glucose, but not L-glucose. And all the plants that produce sugar also produce D-glucose, but never L-glucose. So that's how everything works consistently on our planet. So this is actually a money-making opposition for all of you. So if you can come up with a mass manufacturing process inexpensive enough to produce L-glucose, you will be an instant billionaire, a trillionaire, because it's made of the same stuff, totally healthy, tastes about the same, but you can digest it. That's 0 calories, right? You see how you can make money of it. And the same goes with the amino acid. They also have two different orientations. And our entire, again, the biomass on the planet is built of the amino acid of only one orientation. But it's pretty likely that if you go and find some other planets with the alien life forms living there, there's a 50-50 chance that their life is built on either this orientation or that orientation, because as far as the chemistry and physics are concerned, there's no difference between them. But once life started on a planet and started to evolve into this evolution tree, we happen to choose one orientation over the other. That's spontaneous symmetry breaking. And as a matter of fact, there was one mission by the Japanese Space Agency that actually sent probe to this asteroid called Ryugu. And that's beyond Mars, it's pretty far away, but it actually managed to take a sample and came back to the Earth. And we actually managed to get a sample of the sand from this the asteroid. And they actually did find the amino acid in it. And so that, of course, raises the hope that there may be life form outside the planet. And there have been this persistent idea that maybe life on a planet, on our planet, have been brought on asteroid or meteor from some faraway planets or moons. And we don't know if that's true. But what they have found is that the amino acid from the sand sample from this asteroid was really 50-50 between left and right. So that strongly suggests that it is not part of an ecosystem, because it hasn't grown to an entire system, which probably relies on only one orientation. So this is probably just a randomly synthesized molecule by some reactions happening in space, rather than the evidence for life. So this idea of spontaneous symmetry breaking is really useful to understand what's going on elsewhere. So in all of these examples, we rely on the same form of the potential, like V equals x squared minus 1 squared, because this function is symmetric under the inversion of x going to minus x. That's the switch between left and right. But you see two minima, so you have two ground states. And when you throw a ball into this potential, you have 50-50 chance of letting the ball get down to this minimum or that minimum. But each time a ball you have thrown into the potential end up choosing one out of the two, and hence spontaneously breaks the symmetry. So all of these examples can be described basically by one equation of this form of the potential. And this is an example of what we call the discrete symmetry, because all you can do is flip. But there are examples where you can have also a continuous symmetry that is spontaneously broken, like rotation. And this is the picture I've taken from an article by the Nobel Foundation when they awarded a Nobel Prize to some of the work related to spontaneous symmetry breaking. And this is what they did. So imagine a pencil, which is cylindrical, and so it's totally axially symmetric. And suppose you manage to let it stand upside down on a table. And if you manage to actually make it really, really precise, then equation of motion tells you that it should stay that way because everything is totally axially symmetric. And of course, in reality, we don't know that's possible because even a tiny shift in the orientation or direction will let the pencil fall down on the floor and then the pencil ends up pointing in one particular direction out of all possible directions it can possibly point to. So that's an example of a rotational symmetry. That's a continuous symmetry. But when pencil falls on the floor, it ends up choosing one direction, and the ground state is no longer respects the rotational symmetry of the original system, and hence a continuous symmetry can also be broken. And they apparently felt that this example is very unphysical and unrealistic. So they presented yet another example of a rod standing up, and you exert pressure on top of it. And to some extent, for a while, the rod will resist your force and just stay put. But when the force becomes strong enough, at some point, the rod would budge. And rod, again, is totally symmetric under rotation. But when it budges, then of course, it chooses one direction to budge or from all other possible directions. And then rotational symmetry is spontaneously broken. That's where a magnet on your fridge comes in. So magnet is made of a whole bunch of spins of electrons in the system. And electrons are not paired between spin up and spin down. And so that each of them carries a magnetic moment of its own. And when the temperature of the system is high, then all the spins are random. So they are pointing in all possible directions. But when the spins when you start to cool the system, then there is a force that prefers spins to be lined up in the same direction. That's the idea called ferromagnet. So once you start to cool down the system, there is some collection of spins that start to line up in one particular direction. Then all the other spins also want to point in the same direction. At the very end of the day, you find all spins in the same system, pointing in the same direction. So even though individual spins can point in every direction, interactions between them is also invariant under arbitrary rotation of the spins. But at the end of the day, they end up choosing one direction. And therefore, the ground state of the system is no longer rotationally symmetric. And that's how the magnet on your fridge works. And same thing happens when you freeze liquid water into cubes of ice. So when something is frozen, I'm not talking about this frozen here, but what I'm talking about is, let's say, the vapor coming out of a volcano. When it's hot, then individual water molecules are moving very fast. And they're moving in a random direction, and there's no particular place in this gas. So the gas is invariant under both rotation and translation. And that's because of random motion of these molecules. But once the water freezes into cubes of ice, ice is a crystal, which means that molecules are lined up in a very neat fashion, like this one. But if you look at this picture, it has a particular orientation. If you rotate the crystal, they are different ground states from what you're looking at right now. And also, each molecule occupies one particular position. If you shift them, again, that's a different ground state of the crystal. So the crystal in a solid actually has undergone a phase transition that both translational symmetry and rotational symmetry have been spontaneously broken in the same way of halibut and magnet. And if you go to other weird phenomena like a superfluid of helium-4, and when you actually go to a very low temperature, then superfluid loses viscosity completely. So it can seep through the tiny holes at the bottom of this vessel. And because there's no viscosity, that's a very weird phenomenon. But the reason why that happens is that the wave function of the system, or to be more precise, quantum field that describes this helium-4, has the symmetry of changing its phase. But when it becomes a superfluid, it chooses a one particular phase for the entire system. And so this change of phase is an asymmetry, but has been spontaneously broken. That's why it leads to this kind of weird phenomena. And when you go to superconductor, that is even further promoted to the change of phase arbitrarily from one position to another, called the gauge symmetry. But once again, this symmetry is spontaneously broken, and that is the origin of this piece of metal losing resistivity, electrical resistivity, below a certain critical temperature. And once actually it loses resistivity, then you can let quite a bit of electrical current flowing through the system without any loss. And so Japan is actually building this maglev right now for commercial transportation. And for maglev, it's a levitation. So entire train got lifted up by a magnetic force so that it can go at an incredible speed, like 400 miles per hour. But if it's actually moving on a rail track, it would shake so badly that the people would be, get nausea and feel very uncomfortable on this. The reason why this can still work is because you levitate the entire train so that it's not sitting on a rail track to minimize the vibration. And in order to actually lift something as heavy as a train, you need to provide a strong magnetic force that would require large electrical current. And then the idea is to use the superconductivity to actually make that happen. So that's the idea of the magnetic levitation train. And so in all of these examples, you have the spontaneous symmetry breaking of a continuous symmetry. So unlike the switching left and right in a discrete fashion, then we draw a potential like this one with this formula. So in this expression, x and y can be freely rotated because x plus y squared doesn't change under rotation between x and y. And that's how you have a potential that has like this continuous set of minima at the bottom of this potential. And once again, if you randomly throw balls into this potential, that will bounce back by this tip and eventually falls down somewhere. And you can choose this, that, or that minimum. And they are all related by the rotation around this axis, but they are different ground states of the system. And so that the symmetry can be spontaneously broken. And this happens also in many systems of the microscopic and fundamental physics. For example, there's an interaction called the weak interaction that is responsible for nuclear beta decay. And this weak interaction has been studied in great detail at an accelerator experiment called LIP that used to sit in the same tunnel where the Large Hadron Collider is doing experiment today. And many people in our department is involved in Atlas experiment of the Large Hadron Collider, and they have discovered Higgs boson. And so using the predecessor experiment called Large Electron-Positron Collider, people could study the nature of this weak interaction in great detail and discovered that the weak interaction is very much the same force as electromagnetism. But there's one big difference between the two. We know electromagnetism is a long-range force. If you hold a compass in your hand, the needle of your compass would be pulled by the North Pole of a planet. So it goes over a long distance. On the other hand, weak force is a very short-range force. It goes only over 10 to the minus 16 centimeter. That's even a thousandth of the size of a proton or neutron. So it's a very short-range force. So how come that the forces of the similar kind, electromagnetism weak interaction, as we have learned over the years, exhibit such a different behavior that one of them is long-range, the other one is such a short-range force. And that's where we actually learn from, again, example of superconductivity. So you might have done this experiment in undergraduate lab, where if you have a piece of superconductor and then it would actually float on a piece of permanent magnet. And that's because the magnetic field cannot penetrate into a piece of superconductor, except for these vortices punching through. And even when they're punching through these vortices, magnetic field can extend only for a very small distance called penetration depth, which may be, say, 100 microns or something. So inside a piece of superconductor, magnetic force has become a short-range force rather than a long-range force it is supposed to be. So that's how we figured, well, maybe our universe is actually a piece of superconductor. We are dipped inside. Something is causing superconductivity in a universe. And as a result, the weak force has become short-ranged, just like the magnetic force in a piece of superconductor. And that's the idea that became the foundation of the Higgs boson and standard model particle physics. So the idea is that Higgs boson is a particle that used to fly about in a random fashion when the universe was very hot. But at some point, it froze in empty space. And we are living in the ice of the Higgs boson. In a case of superconductor in the laboratory, what you see is that the pair of electrons end up causing a condensate, and that's causing the magnetic field to become short-ranged. In the same way, our universe has a condensate of the Higgs boson frozen in ice, and when the weak interaction wants to go to act on a distant body, then the carrier of the weak interaction, called the weak boson, gets constantly bumped around and disturbed by this Higgs boson condensate, so it doesn't go very far. And that's how it became a short-range force. On the other hand, photon that carries the electromagnetic interaction doesn't notice that it's flying through the ocean of the Higgs boson, because photon interacts with anything that has electric charge. But Higgs boson does not have an electric charge, that's neutral. So photon doesn't realize that it's moving inside this ocean of the Higgs boson. It just keeps going the speed of light. So that is the difference between the weak interaction and electromagnetic interaction, why the weak interaction has become so short-ranged even though it's of the same kind as the electromagnetism. And in addition to all these forces, even electrons inside your body is being disturbed constantly by the Higgs boson. So electron actually wants to go at speed of light, but it keeps bumping on the Higgs boson, filling up the entire universe, gets slowed down, namely it acquires a mass. And that's why it can go slowly and happily move about inside the atoms in your body. So if the Higgs boson weren't there, the electrons would be moving with speed of light. And in fact, we need exactly just the right amount of the Higgs boson to be condensed in the universe today, because if there are too much of them, the weak interaction really doesn't go anywhere. Then the weak interaction doesn't happen, then sun doesn't burn to produce the nuclear fusion process, and we can't live in that kind of universe. On the other hand, if there are too few of them, then weak interaction can go over long range. Then the whole universe becomes too radioactive for us to live either. So we need to have the just right amount of it. And I don't know, and nobody knows why we have this just right amount of Higgs boson in the universe today. That's something people are trying to understand better by doing more research on that. But the point here is that electrons inside the atoms, if they weren't for the Higgs boson, if it evaporates at an instance, they start moving at the speed of light, the atoms would disappear, and also our bodies would disappear in a nanosecond if the Higgs boson weren't there. So the Higgs boson is very important for us. It is keeping a body in one shape by filling up the entire universe like a swarm of superheroes. But we still don't know who exactly they are. Why are they frozen in the universe today? And hence, why do we exist today as a life form in this universe? And one thing I'm really jealous about our friends in condensed matter physics is that they can reproduce the Higgs boson in a much cheaper experiment. And the OSC costs probably like $5 billion to build. But in condensed matter labs, like in this case of a high power laser, what this scientist did is to take a special superconductor, and as I told you already, based on the same idea of physics, and if you put enough force on it, then the condensate in the superconductor can start to bump up from the minimum to somewhere else. And once it's bumped up, then it starts to fall down and go swish, swash, 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 and start to oscillate for a while and eventually settle down back to the minimum. So that's something you can do with a terahertz laser with a femtosecond pulse. So you whack a superconductor with the femtosecond pulse laser, system gets excited, and you see this vibration going on for a while. And this frequency corresponds to the mass of the Higgs boson in a superconductor. So it's based on the same idea. So what I try to tell you so far is that this idea of spontaneous symmetry breaking seems to be happening pretty much everywhere in our understanding of physics today. And so there's some universality or universal laws governing all of these systems. And one such universal law is stated as the Goldstone's theorem, and according to Jeffrey Goldstone at MIT. So what he told us, together with his collaborators, is that when a continuous symmetry is spontaneously broken, there appear the same number of massless particles or gapless excitations as the number of broken symmetries. And this excitation has certain energy and momentum, and they are related by a linear relationship between energy and momentum. We call this a dispersion relation. So Goldstone bosons have to have this linear dispersion, and we call them Nambu Goldstone bosons. And this fact that you have this massless or nearly massless in some cases excitations is manifested in this picture of an experiment Barbara Jacek is doing in our department called in Alice experiment at CERN. And what she does is to take a nuclei of lead, which is a fairly big sized nuclei, and accelerate them to incredible speed and smash them against each other. And once they reach this incredible energy and density, then the protons and neutrons inside nuclei start to melt into a soup of quarks and gluons, and they start to expand, And once they start to expand, of course, they start to cool like a big bang. And eventually, these quarks and gluons start to become bound states into a particle called pion. And this is the flow of pions coming from a single collision. You produce so many particles in a single collision. And that's simply because each of them are very, very light compared to the standard of this kind of strong interaction physics. And that's because we believe the pion is one example of this Nambu Goldstone boson. And that is based on this idea called chiral symmetry that seems to be spontaneously broken also in our universe today. And this kind of strong interaction physics is very difficult to understand because once this interaction is strong, you can't rely on perturbation theory to do any calculations. Everything becomes strongly correlated and non-perturbative. So recently, I've been working on an idea how to actually address this kind of strong interaction physics, getting inspired from our friends in atomic physics like Dan Stamperker. So when you have a system of Fermi gas, and when the fermions are non-interacting, then that gives you just a Fermi gas, like in the piece of metal at the normal temperature. But once the fermions, electrons in this case, have some weak attractive force among them, then that will destabilize the Fermi surface and then turns into a superconductor that is called the BCS state. But after you start to making this weak, the attractive force stronger and stronger, at some point, you'd rather talk about the two fermions become bound into a boson, and that boson undergoing a Bose-Einstein condensate. But they are continuously connected as you keep increasing the force of the attractive force between the electrons. So what you can learn for the weak interaction of the BCS state, that's something you can really work it out because the interaction is weak, can all the way carry over to the strong attractive force because there's no phase transition between them called crossover. So in the same way, we are trying to understand the theory of strong interaction called QCD, which nobody can even compute anything really out of it, except for some giant supercomputer simulation. But if you actually introduce a new symmetry called supersymmetry, and the supersymmetric version doesn't seem to resemble the real world at all. But the minute you break it a little bit, then all of a sudden, it starts looking like what we see in the real world about the behavior of the strong interaction. And then I can hope that I can keep making the breaking of supersymmetry larger and larger so that eventually I can take it to infinite so that I recover the real world strong interaction physics. And as long as they are continuously connected, what can happen here can be learned by doing a perturbative calculation over here. So you can actually get some good understanding of why you never see an isolated quark called confinement, why the chiral symmetry spontaneously broken, as I mentioned on a previous slide. So that's something I'm actually doing research with a bunch of students here. So the idea is that the real world physics is difficult to understand. That's a real cow. So the first thing you do to introduce a symmetry to make it a spherical cow, and spherical cow is something you can understand, but it doesn't look like the real world at all. But the minute you put in just a little bit of breaking of symmetry, then you can start picking up all the right features of the real cow. Then you can understand what's going on, at least qualitatively. So that's a technique I'm using here. And we are still learning a lot about how this kind of theory actually works in practice. So all of these things are fairly universal theme throughout physics. And the Goldstone theorem I mentioned earlier seems to work in many, many different systems. So I mentioned crystal, when you cool the gas of water vapor into a solid ice cubes. And once they line up in this neat crystal, then there is a translation symmetry that is spontaneously broken. So you have translation symmetry in this direction, that's broken, and another translation symmetry in this way, that's also broken. So the idea of Goldstone theorem is that when a symmetry is spontaneously broken, you can kick the system using the symmetry. And once you actually kick the system with this translation on this end of the crystal, then what you see is the crystal starts to vibrate like this one. And that's a sound wave. And quantum version of that is the phonon. and it is gapless, namely energy goes to zero when momentum goes to zero, and the relationship is indeed linear. And for the other translation symmetry, again, you kick the system like this one, then system again starts to oscillate like this. That's yet another sound wave called transverse phonon. And once again, you see a linear relationship between energy and momentum. So you find a gapless excitation for each of the translation mode, which is spontaneously broken according to the theorem by Goldstone. And for each case, energy goes linear with the momentum. So that seems to work very well. I mentioned the superconductivity as another example of spontaneous symmetry breaking. So that is the symmetry of changing the phase of this quantum field that describes the whole collection of atoms. And that has an expectation value. So it has chosen a one particular phase, and this symmetry has been broken. And that symmetry leads to also gapless excitation. Here you see a linear relationship between momentum and energy, and goes to zero energy, hence gapless. And also the boson condensate of cold atoms exhibit the same behavior. And this spectrum is something you can understand very well once you actually study QFT, which some of people here have done, called Bogoliubov spectrum. You have seen that before. So again, the same idea seems to work everywhere. And this kind of the symmetry breaking is also believed to happen at the core of the supernova explosion called neutron stars. And neutron stars explodes. When the star dies, or when a heavy star dies at the end of its lifetime, it starts to collapse to a very incredible dense material called neutron stars. An envelope bounces back and it explodes and becomes a supernova explosion. And what you're seeing in this picture is a remnant of such supernova explosion that spurts out all kinds of chemical elements into outer space. And so you are actually born out of this stuff. So the first generation of stars died, but before they died, they synthesized very bigger and bigger elements from the original hydrogen and helium into carbon, oxygen, nitrogen, and so on and so forth that had been spread out into the empty space. They got collected back again by gravity to have the second generation of stars. They also undergo this nuclear synthesis and the fusion process at the core. And then the elements get formed into calcium and iron. They spread out into the empty space again. And they got collected back again by force of gravity. And that's our sun. So when the solar system was born, there was quite a bit of abundance of all of these heavier elements, so that you have your bone made of calcium, you have your blood made of iron, and they all came from that stuff. And at the very core of this, it is believed that neutron star is in a BCS state, so that you have the pairing of the two neutrons, which is condensed, and that actually leads to this kind of gapless excitations at the core. But now comes a little problem with this whole idea. So if you look at the piece of magnet on your fridge, they are ferromagnet. So when the spins are lined up in the same direction, you can lower the energy because of minus sign. There's another system called antiferromagnet where the sign is positive, so the spins rather want to be anti-aligned. So the ground state would look like this for antiferromagnet, and ground state looks like this for ferromagnet. But in both cases, even though the Hamiltonian is totally invariant under arbitrary rotational spins, because it's a dot product of two vectors, you can rotate them arbitrarily, but the ground state chooses one particular direction. So system is still invariant under this axial rotation, but it doesn't respect the rotation this way anymore or that way anymore. So two symmetries are spontaneously broken in both of these systems. And as a result, you would expect two gapless excitations in this system with a linear dispersion if you listen to Jeffrey Goldstone. And indeed, for antiferromagnet, you do find two gapless excitations in the spectrum. But for ferromagnet, it turns out that there's only one. And also for dispersion relation, for the antiferromagnet, it's really linear as predicted, but ferromagnet is quadratic. So Goldstone theorem doesn't seem to work. And in fact, for the ferromagnet, again, the same idea that if you have broken symmetry, you kick the system to produce an excitation. If you kick the system with the sideways rotation, then you would expect this kind of excitation should exist. If you kick the system with this rotation, you would expect this kind of excitation to exist. But for actual ferromagnet, you find only one mode, which looks like this. So something is amiss. And Heisenberg model for ferromagnet have been known for decades, but somehow something had been lost. And as long as the ferromagnet is sort of isolated exception to the rule, people might have been happy about it. But when people start looking into this behavior of neutron stars, the nuclear physicists start looking into it, and they discovered that there seems to be spontaneous symmetry breaking with abnormal number of Nambu-Goldstone bosons. So similarly to ferromagnet, they found fewer degrees of freedom than the number of broken symmetries. Again, something is wrong. Here's another paper talking about abnormal number of Nambu-Goldstone bosons. Now back to the condensed matter physics, this abstract also talks about the abnormal number of Nambu-Goldstone bosons. So something is missing in our understanding. And Nambu himself wrote a paper. He passed away several years ago, but back in 2003, he has written a paper on spontaneous breaking of Lie and Codd algebras. And after reviewing this basic concept, as I mentioned earlier, he says, there are, however, exceptions to the above theorem. So there are exceptions. And then theorem is not true. And I was actually very happy to see this paper because Nambu, I knew him to some extent, was a really humble man. And he was very softly spoken. He never bragged about himself. And even his students, I know two students of his, they were not aware when they were students of Nambu what a great physicist he was, because he never bragged about it. Only after he died, oh, he was actually a great physicist. But even he referred to Nambu-Goldstone bosons with his name in it. So at least he has some sense of a pride in it. So I was very happy to see that. And the fact that there are these exceptions to the rule, I actually didn't know when I was teaching graduate level QFT class on 1 year, but there was a student who happened to know very well about condensed matter physics. And so he raised his hand and said, "Professor, you're wrong." "What do you mean I'm wrong?" So I had to sit down with him after class and try to understand what he meant. And then I realized, okay, I don't understand this. So, and he had some ideas, but that was not actually concrete yet, enough yet. And we sat down together, and eventually, in about a week, we came up with a new theorem, which seems to explain all of this. So the idea is actually, in the end, once I understand it, it was very simple. So in the case of an antiferromagnet, spins are anti-aligned. So when you look at the overall expectation value, they cancel against each other. So expectation value of spin is 0. On the other hand, for ferromagnet, they all add up. So you have a big expectation value of spin in z direction. And as you know from quantum mechanics class, spin in z direction can be written as a commutator of spin in x and y direction. And spin in x direction is what was supposed to give you the excitation by doing this kick. Spin in y direction is this kick. We thought that would give you a 2 independent degrees of freedom. But as you know, when the commutator of two operators is non-zero, like x and p together describe a particle in one dimension, right? So in this case, Sx spin in this rotation and Sy this rotation are not independent from each other, but together they describe a 1 degree of freedom. So that actually turned out to be the understanding how we can understand why there's only 1 degree of freedom here, why there are 2 degrees of freedom here. The fact that there is the expectation value or not makes the whole difference in the behavior of the system. And all of them can be combined into a single line in quantum field theory. And whenever you have this expectation value of certain asymmetry generators, then you have this extra term. And once you have this extra term, it looks like the Lagrangian is written in the form of PQ dot minus Hamiltonian, because this is the first order in time derivative. And then you know this is Q and this is P, so they are not independent from each other. On the other hand, when you don't have this term, and this is Q dot Q dot, so each Q would have their own P, and therefore different symmetries are independent from each other. So that's the way you can understand all of these things, which hinges on whether this commutator vanishes or not. And if this commutator is non-zero, then two of them giving you 1 degree of freedom. So you have to subtract that from the total number of the broken symmetries to understand how many gapless excitations there are. And this first term is not allowed if the system is Lorentz invariant. That's why Goldstone didn't think such a term could be there. But in a magnet on your fridge, it's not Lorentz invariant. It's not relativistic. So this term actually is allowed. And as a consequence, you have fewer number of gapless degrees of freedom. And also, you can see why the relationship between momentum and energy is quadratic. If you look at this term, first order time derivative, in quantum physics, that's energy, right? And here you see second order space derivative, again in quantum physics, that's momentum, right? And this is momentum squared that goes together with energy. And that's why energy goes like quadratic in momentum. That's it. So it turns out that once you know that this is what's going on, in every simple example where people talked about this abnormal number of Goldstone bosons, they all agree based on this new theorem. So we were very happy to publish this in Physical Review Letters. And I also got to learn a lot by talking to mathematicians on this campus. Alan Weinstein is a specialist on symplectic geometry. It turned out that the correct mathematical language for this is what is called pre-symplectic structure on homogeneous spaces, which is a very obscure math, even most mathematicians haven't heard of, but that actually turns out to be the right description. And so there is actually many different interesting examples of this. So when you have the Bose-Einstein condensate of atoms with spin 1, these spins may also have some kind of ferromagnetic interaction. And being spin 1, you can rotate 3 different orientation spin, right? The spin 1 can come with SZ being +1, 0, or -1. So you have 3 different possibilities of spin, and you can freely rotate among these 3 components. And each of them is again a quantum field, so you can change its phase. So you have 3-dimensional rotation and the phase rotation of the field. But it ends up acquiring very weird expectation values. And if you actually write this in terms of real component, imaginary component, it's a little easier to understand. This phase rotation is the rotation between real column and imaginary column. So that's rotation along this direction. 3-dimensional rotation of space is rotation in this direction. And only one particular rotation done together between X and Y coordinates here and between the 2 columns remain unbroken. So out of 3 + 1 symmetries, you have only 1 remaining symmetry. So you have actually 3 broken symmetries. But you don't have 3 gapless excitations. You have 1 with the linear dispersion, another one with quadratic dispersion, because the one with the quadratic dispersion is because of the pairing I mentioned on a previous slide. So this counts for 2 symmetries instead of 1. 2 + 1 is the 3 broken symmetries. So I was very excited that this system really put all of these possibilities together in a single system. So I urged Dan Sampakan to really prove that you have this quadratic dispersion in this system. And he measured that. And indeed, you see this parabolic curve for the excitation. So it is quadratic. And if you want to know more about this, there is some special fiber bond structure from the topology of this the homogeneous spaces you can look into, and I don't get into that, but at least you can see that this actually gives you the correct mathematical description of all of these systems. And once you know the language in math, you can even list up all possibilities of what pairing is possible among different symmetry generators. But once you have learned that something about these broken symmetries and mixed up in a very interesting way, I try to come up with a way of actually using it. And one of my recent research is to use the system of helium-3 in superfluid. Helium-3 is a fermion, but they have the weak attractive force between them, so they can also undergo phase transition to become a superfluid in the BCS state, just like the superconductivity among the electrons. You have, again, complicated autoparameter. It's now the autoparameter is 3 by 3 complex matrix, but nonetheless, you know what's going on there. And once you go to a very low temperature of millikelvin in a magnetic field, they can become sort of like a ferromagnet. And using this magnetic orientation, then you can try to detect a new particle that might couple to nuclear spins, like axion, that is meant to be a candidate for dark matter in the universe around here. So in principle, once you have this the superfluid helium-3, you can use that as a medium detecting axion, dark matter in the universe. And we have shown that you can even reach the sensitivity as predicted by theory. So that's how all of these ideas are actually connected and even can be useful. And I have to skip some of the more developments I actually have gone through, like why another candidate of dark matter could be just like pions, it's a composite objects, which may give you a dark matter, correct dark matter abundance. And for that purpose, I'm actually just started to build finished building a new spectrograph for a major telescope that we can actually look at the mass distribution in dwarf galaxies. One can also start thinking about why you exist at all. Big Bang started with a huge energy, and when an energy turns into matter, you produce the equal amount of matter and antimatter 1 to 1. But if they stayed that way, eventually they would meet and go back to pure energy, and the universe would have been empty, then you wouldn't be here today listening to me. So something must have happened. Namely that when the Big Bang produced so much matter and antimatter, say like 1 billion each, at some point, somebody somehow must have managed to pick one antimatter out of a billion and turn that into matter somehow, so that when they meet, pretty much all of them will annihilate each other, but very few of that would remain to date, and that's supposed to be you. So how did that happen? So the best theory we have today is called leptogenesis, because when you want to transform matter into antimatter, you can't use a charged matter particle like electron, because matter particle has charge Q, let's say negative E in the case of electron, and antimatter has the opposite charge. In the case of positron, that's positive E. So because the electrical charges are conserved, the matter and antimatter can never turn into each other. But the only exception to that idea is the particles named neutrinos. Even though it's a matter particle, has no electric charge, 0. So antineutrino has charge -0, that's also 0. So in principle, they can turn into each other. Matter neutrino can turn into antimatter neutrino and come back. And that's a process called neutrino double beta decay. Many people in the department, like Yuri Kolomensky and Gabriel Orebigan, are actually doing experiments looking for that process. We haven't found it yet. It's known not to happen even once in 10 to 26 years. But we are patient physicists. We're looking for the process to happen eventually. But if that's the case, the neutrino may have played a role of reshuffling antimatter into matter so that we could survive. And that's the idea called leptogenesis. This due to these two gentlemen recently. So neutrinos could be superheroes who could have actually saved us from complete annihilation. And if that idea is true, then we need actually heavier counterpart of the neutrino produced right after Big Bang, very heavy object, decaying very soon. But in this mass region, then you could actually explain this phenomenon. But to test it is very difficult when you're referring to physics at very high energy scale. But it turns out that there is a way, and that's another thing I have actually worked on recently. So if we really would like to test it directly by using high energy colliders to reach up to 10 to the 14 GeV energy, based on current technology, the size of the collider would be as big as this one. That doesn't sound practical. So we need to find some other avenues to do that. But the other avenue is the following. So when these heavy neutrinos are produced in the early universe, that might be also due to yet another phase transition, like superconductivity. And superconductor has this magnetic field punching through it. So if the universe becomes a superconductor with a magnetic field punching through it, that becomes an object called cosmic strings. And when they're produced, they would like to simplify itself because energy is proportional to its length. They would like to become as short as possible. And as they try to do that, they can radiate gravitational waves. It turns out that that may appear at the level detectable by future missions from this network of cosmic strings due to these heavy neutrinos born right after the Big Bang. So what I want to tell you is that all of these different systems happen to have the same common theme based on spontaneous symmetry breaking. And once you understand it, you can think about how to use it, or you can even use it to model the physics that are in the universe to understand why we have survived the Big Bang. And that's the way that you can tie things together is what really like about physics. That's why physics is fun. Okay, that's it. Thank you.
Any questions?
I can stick around after that. Yeah. 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 So the question was that spontaneous symmetry breaking, how does it happen? So when you actually start with a system at a high temperature and eventually cool it down, then the system will start looking for a ground state it can settle down to. But then the system finds there are many, many possibilities of the ground states, as we talked about before, but it needs to pick one. It has to settle somewhere. And that's when spontaneous symmetry breaking happens. That's why it's called spontaneous. You don't need to put any forces on it. It just happens, system happens to find a minimum on its own and hence spontaneous. Yes.
Does this spontaneous metric breaking depend on the potential energy form we assume? Or if we use a different form, different shape, will we have different world?
Right. So the question was whether spontaneous symmetry breaking depends on what kind of the potential we assume about the system. And indeed it does, because if you have a potential like this one, then it has many, many different minima, and the system needs to find somewhere and ground state somewhere, and then breaks the symmetry. But if you go up to high temperature, then this potential changes its shape so that instead of having a minus sign here, it ends up finding positive sign. So then that the minimum is really at this origin in X and Y and rises parabolically around it. And there's only one minimum of the potential. That's why if you go to high temperature, typically symmetry is restored like the gas of the water vapor. But when you go to lower temperature, the system finds many, many ground states, like the cubes of ice. And that is the idea called Landau theory of phase transition.
Okay, if anyone has any other questions, please feel free to walk up afterwards.
Yep. So I stick around for another 20 minutes here. Okay, thank you.